So now, let's talk about the factors that affect solubility. So the factors that affect solubility, before we talk about the first one is actually the temperature. Yeah, temperature affects solubility of a particular ionic compound. Now, the second one on the list, before they discuss about the temperature a lot, now the second part on it is what we refer to as the common ion effect. So common ion effect. So if you're talking about common ion effect, what literally comes in mind? If you can look at the word common means what? We are having it in what? Both situations. And ion, it means that now we are having an ion that is common in both of something, and its effect of the effect of this common ion on that particular what? Ionic compound. So let's say now we are having a solution. If you're having a solution such as NaCl solution or salt solution, a solution that is made up of sodium chloride, right? So now you are having sodium chloride solution, or you are having a solution that is what? Made up of what? A salt or a chloride salt. Then if you should add a salt that contains, let's say we are adding AgCl, assuming that AgCl is actually a soluble salt, and we are adding this AgCl into a solution, then the common ions here that we are having is what? Cl and Cl. And if you're having Cl and Cl in the same solution, then it means that the concentration of this Cl is going to increase, and it will affect its solubility. Affecting its solubility doesn't affect only chloride alone, or it doesn't affect only the Cl alone, but it affects the Cl together with the salt that is coming with, together with its cation that is coming with, together with the agent. So AgCl as a whole will be affected. So now let's try and talk about, let me put it in a similar way or in a nice way that will make you understand it. If you're having a solution, and this solution is made up of a cation and maybe a chlorine. So now you're having chlorine ion already in the solution. And now you are dissolving a salt. You are dissolving a salt such as NaCl into this particular solution. Now, you dissolving this into the solution that already contains Cl minus. Then the common ion here is Cl minus. So if you're having Cl minus here, and now you are dissolving NaCl also into this solution, it's like you consider a room where it can accommodate only a specific number of people, and you are also including another person also into the same room. Then it means that one needs to get out, and if it is getting out with what? With its company. So the same thing applies here. If you're having NaCl into this particular solution, it means that the solubility of this, the solubility here is actually its ability to dissolve fully. Its degree or its extent of dissolution is going to decrease because we are having some of this ion already in the solution, and now we are introducing it. So now this chloride ion, its solubility is going to decrease, and if it is decreasing, it will be decreasing with what? With the NaCl. It is decreasing as a whole. The whole NaCl salt will rather be decreasing in terms of its solubility. But remember that the Ksp will remain the same. The Ksp will not change. So if you're having AgCl, for instance, AgCl being a salt, if you split it, or AgCl in a particular solution, it will give you Ag plus and Cl minus at equilibrium. Now, let's say the Ksp of this particular AgCl is 1.6 times 10 raised to the power negative 5. So if this KCl is let me use raised to the power negative 10 for it to be reasonable. 1.6 raised to the power times 10 raised to the power negative 10. If this is the Ksp of the salt, and now we have increased the this AgCl has now been dissolved in a solution that already contains Cl minus. For instance, if you have this AgCl has now been dissolved into this solution that contains Cl minus, and now the concentration of this Cl minus is, let's say, 0.01. If this is the concentration of the Cl minus already in the solution, then we can find the solubility. You remember that KSP is equal to, for this, if you are writing the expression, then our KSP is equal to S times S, right? Giving you S squared, where S is actually the solubility, or the S is represented by solubility, denoting solubility. So if you know your KSP, then you can find S by just making the square root of what KSP. So your solubility, S, will be equal to your square root of your KSP. And the solubility, remember that this S, the value of this that you are finding, is the same thing as the solubility of this. And also the same thing as the solubility of this. And I already said that solubility is the same thing as concentration. So the concentration of this, at the same time, the concentration of this is what you are finding by the square root of this KSP. And this KSP, the value of this KSP will actually give us what? 1.6. So if you find the square root of this value, the value that you get here will actually be the same as the solubility of Ag and also solubility of this. So now if you are introducing this AgCl also into the solution, then now let's try and look at the effect of this common ion on this AgCl, because its solubility is going to decrease. Remember that now there's an assumption that I want you all to pay attention to. Where should I clean? Let me clean this part. Remember that this one is going to give you a certain value. Let's say it's going to give you a certain value times 10 raised to the power negative 5. So you see, so the concentration of this, or the solubility of this, and the concentration of this, so the concentration of Cl minus from the salt is something times 10 to the power negative 5, and this one is times 0.01. If you add these two, you are still going to get what? 0.01, because this value is very small, that if you add this S to this, you are still going to get 0.01. If you really don't get it, if you really don't get this assumption, try a bucket of water. If you're having a bucket of water filled with halfly filled, and now you go and dip your hand into, let's say, another water, and you come and put that drop in that bucket of water, will the volume really change? Will the volume of the water really rise? It won't rise. There will be no appreciable change in the volume of this bucket of water, because the one that you've come to add to this huge number is very small to an extent that the 0.01 is still the same thing as the 0.01 plus, let's say, 0.00000 something will still give you the same thing as 0.001. For instance, if this one is giving you 3.6 times 10 raised to the power negative 5, then 3.6 times 10 to the power negative 5 plus 0.01. If you use your calculator, you are still going to get 0.01. So that's all what I'm trying to mean by the assumption that I've referred to here. So now that if you using the common ion effect, you are going to realize that you know the concentration of Cl. So now your new KSP expression, where should I clean? So now your new KSP expression will be equal to the concentration or the solubility of Ag plus and also the solubility of Cl minus. But you know the concentration of this, because we've realized that that small number plus 0.01 will still give you 0.01. Then our KSP will be equal to Ag plus solubility of it, then 0.01. So now we can find the solubility of this Ag. So now this Ag plus its solubility will be equal to your KSP times 0.01, which will give you 1.6 times 10 to the power negative 10 divided by 0.01, and it will give you 1.6 times 10 raised to the power negative 8. If my calculations are right, it will give you 1.6 times 10 to the power negative 8. And giving you 1.6 times 10 to the power negative 8, it means that now the salt itself, the solubility of this AgCl is now what? 1.6 times 10 to the power negative 8. But initially, if you are finding the solubility of this, given the KSP without dissolving it in the solution that contains the Cl minus, if you are finding the solubility, then the solubility will be equal to what? The square root of what? KSP, which will give you something times 10 to the power negative 5. But now we are having it to what? Times 10 to the power negative 8 after we've dissolved it in what? The Cl minus. remember that we're still using the 1.6 times 10 to the power negative 10 because I already told you that KSP does not change. KSP does not change. So now this is what I refer to by the common eye effect. So common eye effect, generally, it decreases the solubility of a salt or an ionic compound. So you see now, because we dissolved it in the solution that contains the Cl minus, now the solubility has decreased from times 10 to the power negative 5 to now raise the power negative 8, and negative 5 and negative 8. Which one is the biggest? Negative 5, right? So now that we are having the new solubility of the salt after dissolving it in a common ion solution to be negative 8, then it means that the solubility of the thing has what? Decreased. Now let's try and talk about the effect of pH on the solubility. Now, in terms of pH, the pH is the last thing that I'm going to discuss here. In terms of the pH, if you are having a pH, if you are increasing pH, what does it mean by you are increasing pH? If you are increasing pH, then it means you are approaching what? Basicity, or you are approaching the basic region. And if you are approaching the basic region, in terms of hydrozonium and hydroxide ions, what are you doing? You are increasing the OH minus. You are increasing the OH minus. If you are increasing pH, you are increasing the OH minus. And if you are decreasing pH, then it means that what you are approaching the acidic region, and also you are increasing the H plus or H3O plus. H plus and H3O plus, they are the same. So if you're having a solution and you add acid to it, automatically you are increasing the acidity, or you are increasing the content of the H3O plus or H plus. And if you add a base to a solution, you are increasing the OH minus, and also you are approaching the basic region. So now let's try and look at the effects of some of acid, increasing the acid, or adding acid to a solution. If you are adding acid to a solution, you are decreasing the pH. So decreasing the pH, what happens to the solubility of a salt? Increasing the pH, what happens to the solubility? Now let's talk about it. If you're having Hg3PO4, this is a salt. If you dissolve it in a solution at equilibrium, you are going to get 3 of the Ag plus and PO4 3 minus. Now this is it. For this particular salt, if you add an acid to it, what are you going to get? And if you add a base to it, what are you going to get? Now let's try and talk about the acidity part. Let's try by adding an acid. If HNO3 is being added to this particular salt solution, what will happen to the solubility? Now we can use two things here. There are two things that we can use. We can use the effect of the pH itself, and we can also use the Le Chatelier principle, which says that in a system of what? Equilibrium, or in an equilibrium system, if there's a change, whether maybe an increase in the pH, or whether maybe there's a change in pressure, there's a change in volume, or anything at all, any change at all that disturbs the equilibrium, the system will adjust itself in a way that it will restore the equilibrium back. So now let's try and look at it. If you add HNO3, HNO3 is an acid. Adding it to it, you are increasing its acidity. And if you are increasing its acidity, you are also increasing the content of what? H plus. So now, if you add HNO3, the general idea is that you've added what? H plus to it. Now, if you add H plus to this particular what? Salt solution, this one is a weak acid, so its conjugate base, what does it come in mind? Acid, base, and salt. Its conjugate base, the conjugate base here will be what? Will be very strong. So if you're having a strong conjugate base, then it can be reduced by this hydrogen, or it can be reduced by this proton. So now you are going to have HPO4, or you are going to have H plus your PO4 3 minus, giving you HPO4 2 minus. So if you're having something like this, now this is what I want you to know. If you're having something like this is not the same thing as this. So it means that if some of this is being reduced by the proton to give you this HPO42 minus, then it means that the concentration of this will be decreasing, because now it is being transformed into another thing. So its concentration will be decreasing. And according to the Le Chatelier principle, if the concentration of this is decreasing, equilibrium is being what? Disturbed. And if equilibrium is being disturbed, the system will adjust itself to produce more of what? This. And how will it adjust itself? For it to adjust itself for more of the PO43 minus to be produced, then this salt must dissolve more to produce the 3Hn plus and also the PO43 minus. And in the process of dissolving more, its solubility is increasing, because we're talking about solubility. Solubility is the maximum amount of solute or amount of substance that should dissolve in the solvent. So if you're having more of this now dissolving to produce this or to restore equilibrium, then we are saying that the solubility of this has increased. So that's how important it is. Now the reaction here is that if you add an acid or if you increase acidity, you are increasing the solubility of the salts. For this particular incident, if you increase the acidity, you are increasing the solubility. And if you are increasing the acidity, you are increasing the H plus in the solution. Now let's try and look at the other part of it, where we are increasing basicity. If you are increasing basicity, what do we actually expect? Let's take a salt, a typical salt like magnesium hydroxide. So, magnesium hydroxide, MgOH2 solid. If this is a salt and we are dissolving it in a solution, the ions that we are expecting to get at equilibrium should be Mg2 plus OH minus, but 2 of them, so that it will balance out. So now that we are having this is a salt, and now if we dissolve this salt in a solution, this is what we are getting. Now, what is the effect of increasing? What will be the effect of increasing its basicity? If you are increasing its basicity, it means that you are increasing, how should I do it? If you are increasing its basicity, if you increase it, you are actually increasing the OH minus content. You see how it is? So this is it. Now, if you are increasing the pH, it means you are increasing the OH content. And also, if you are increasing the OH minus content, then it means that you are approaching the basic region. Now, if you are introducing OH minus, we can explain this thing in 2 ways, and it will still give us a valid observation. If you are introducing OH minus, first of all, common ion effect can explain it. Secondly, you can also talk about the other way around, where you are using the Le Chatelier principle, the system will adjust itself. If you are introducing OH minus, let's say that we are not introducing OH minus directly, but let's say you are introducing sodium hydroxide, common ion effect, because this OH minus there, common ion effect. Also, if you are introducing maybe a salt that reacts with water to produce OH minus, it's still the same thing. If you are introducing ammonia too also counts for the same thing, because if you introduce ammonia to it, this time around they might not give you, let's say, adding OH minus, but they'll ask you that adding NH3. Adding NH3 is the same thing as what adding OH minus, because this is a Bronsted-Lowry base. Bronsted-Lowry base will then react with water to give you what NH4 plus and OH minus. So this OH minus is still what in the solution. So in turn, we are adding what OH minus also to the solution. So if you are increasing the OH minus, you are adding a base to it or whatever. There's a common ion effect. You can use the common ion effect to explain it. Because if you add this OH minus, the concentration of the OH minus in the solution will now increase, and it will affect equilibrium. So if it is affecting equilibrium, this will be disturbed, and for this being disturbed, it means that more of this has been produced. So now some of this OH minus will now be reacting with the magnesium to give you back your MgOH, or it will give you back your magnesium hydroxide salt. So instead of you having more of the salt dissolving, you are rather having more of the salt precipitating out, because now you are having more of the ions on the product side, and it's going to react with the magnesium or the cation to give you back your salt. So this is what we mean by the common ion effect and also the effect of pH. The effect of the pH and the common ion effect, they are literally the same, but not the same because the explanations to it are different, and they are different in their ways as well. So with this explanation, solubility as a topic is very, very simple. So I'll see you all in the next chapter of my video, where I'll be explaining more and solving questions on solubility as well, and also its effect, how to know whether there will be a precipitate being formed or there will be no precipitate being formed. All depends on the comparison of the KSP values. So with this, I thank you for getting time watching my video and also spending most of your time on it, trying to get the understanding. And I also wish you the best of luck in your understanding in terms of solubility. So I'll see you all in my next video as well.